Mars, the fourth planet from our Sun, holds within its rusty surface the secrets of planetary evolution, the whispers of ancient waters, and perhaps even the faint traces of life itself. Tonight, as you drift into peaceful slumber, let the complete story of this enigmatic world unfold before you, from its violent birth to its possible future as humanity's second home. In the beginning, there was only dust and gas swirling in an immense disk around our young sun. This was the solar nebula, a vast cloud of material left over from the sun's own formation, and within this cosmic maelstrom, the planets of our solar system would slowly take shape. The story of Mars begins here, in this primordial disk, approximately 4.5 billion years ago, when the universe itself was already 9 billion years old. The process that would create Mars started with the tiniest of particles, microscopic grains of dust no larger than smoke particles drifting through the disk. These grains, composed of silicates, iron, and various ices, moved through space in gentle orbits around the infant sun. As they traveled, they occasionally bumped into one another, and when they did, something remarkable happened. Through the weak force of electrostatic attraction, these grains stuck together, forming slightly larger particles. This process, known as accretion, continued for thousands upon thousands of years. The particles grew from dust grains to pebbles, from pebbles to rocks, and from rocks to boulders. As these objects grew larger, their gravitational pull increased, allowing them to attract more material from their surroundings. The larger they became, the faster they grew, in a runaway process that would eventually form the building blocks of planets. In the region where Mars would form, approximately 1.5 times farther from the Sun than Earth's current orbit, conditions were particularly interesting. This distance placed the forming planet in what astronomers call the snowline region, where the temperature was cool enough for water ice to remain solid, but warm enough that other volatile compounds could still exist in gaseous form. This unique position would profoundly influence Mars's composition and evolution. As the proto-Mars continued to grow, it began to dominate its orbital neighborhood. The growing planetesimal, as these planetary building blocks are called, swept up smaller objects in its path, incorporating them into its expanding mass. Each collision added not only material but also energy, heating the young world from within. This process of growth through collision and accretion continued for approximately 10 to 20 million years. A mere instant in cosmic terms, but an eternity by human standards. The heat generated by these constant impacts, combined with the decay of radioactive elements within the planet's interior, caused the young Mars to melt partially. This molten state allowed the heavier elements, particularly iron and nickel, to sink toward the center of the planet, while lighter silicate rocks floated toward the surface. This process, called differentiation, created the layered structure we see in Mars today. A dense metallic core, surrounded by a rocky mantle, and topped with a thin crust. The core of Mars formed relatively quickly, within the first few million years of the planet's existence. Scientists believe that Mars's core is composed primarily of iron, with significant amounts of sulfur mixed in, giving it a lower melting point than Earth's core. The presence of sulfur in Mars's core is one of the key differences between the red planet and our own world, and it would have profound implications for Mars's geological evolution. As Mars continued to grow and evolve, it faced competition from its planetary neighbors. To the inner solar system lay the growing Earth and Venus, massive worlds that would eventually dwarf Mars. To the outer solar system, beyond what would become the asteroid belt, the giant planet Jupiter was forming, its immense gravity influencing everything around it. Mars found itself in a challenging position, caught between these larger worlds, competing for the remaining planetary building materials. Jupiter's influence on Mars's formation cannot be overstated. The giant planet's powerful gravity disrupted the orderly accretion process in Mars's neighborhood, scattering many of the planetesimals that Mars might otherwise have absorbed. This gravitational bullying by Jupiter is one reason why Mars ended up being so much smaller than Earth or Venus, with only about 11% of Earth's mass. Had Jupiter formed later or in a different location, Mars might have grown to be a much larger world, perhaps even Earth-sized. The early solar system was a chaotic place, with planetary orbits still shifting and adjusting. Computer simulations suggest that Mars may have actually formed closer to the Sun than its current position and migrated outward over time. This migration would have been caused by gravitational interactions with other planets and the remaining disk material. Such orbital evolution was common in the early solar system and helps explain some of the unusual features we observe in planetary orbits today. During this tumultuous period, Mars was constantly bombarded by asteroids and comets. These impacts delivered not only additional mass to the growing planet, but also volatile compounds, including water, carbon dioxide, and nitrogen. Many scientists believe that much of Mars's water may have been delivered during this period, carried to the planet by water-rich asteroids and comets from the outer solar system. The surface of young Mars would have been a hellish landscape, completely unlike the cold desert we see today. Rivers of molten rock flowed across the surface, while the sky above glowed with the constant rain of meteors. The atmosphere, if it existed at all, would have been composed primarily of hydrogen and helium captured from the solar nebula, along with volcanic gases released from the planet's interior. As Mars cooled and solidified, it began to develop its first true crust. This primordial crust was probably composed of basaltic rock, similar to the ocean floor on Earth. Evidence of this ancient crust can still be found today in Mars's southern highlands, which represent some of the oldest terrain on the planet. These highlands are heavily cratered, bearing the scars of billions of years of impacts, each crater telling a story of the violent early days of the solar system. The formation of Mars's crust marked an important transition in the planet's history. With a solid surface in place, Mars could begin to develop more complex geological features. Volcanoes began to form, releasing gases from the interior and contributing to the development of an atmosphere. The largest of these volcanoes would eventually become Olympus Mons, the tallest mountain in the solar system, though its formation would come much later in Mars's history. The magnetic field of early Mars deserves special attention in our story. As the planet's iron core cooled and solidified, convection currents within the liquid outer core generated a global magnetic field, similar to Earth's magnetic field today. This magnetic dynamo would have been crucial for protecting Mars's early atmosphere from the solar wind, the stream of charged particles constantly flowing from the sun. The presence of this magnetic field would allow Mars to retain a thick atmosphere and eventually liquid water on its surface. Evidence for Mars's ancient magnetic field comes from spacecraft observations of magnetized rocks in the planet's crust. These rocks, primarily found in the southern highlands, retain a record of the magnetic field that existed when they formed. The pattern of magnetization suggests that Mars once had a strong global magnetic field, perhaps even stronger than Earth's current field. This magnetic shield would have been essential for the development of the warm, wet conditions that we believe existed on early Mars. The timing of Mars's core formation and the generation of its magnetic field had profound implications for the planet's evolution. Unlike Earth, where the magnetic dynamo has operated continuously for billions of years, Mars's magnetic field appears to have shut down relatively early in the planet's history, perhaps around 4 billion years ago. The reasons for this shutdown are still debated by scientists, but the consequences were catastrophic for Mars's atmosphere and climate. As Mars completed its initial formation, it had achieved a mass of approximately 640 billion trillion kilograms, making it the fourth largest terrestrial planet in our solar system. Its diameter of about 6,800 kilometers made it roughly half the size of Earth. But this smaller size would prove to be one of the key factors in Mars's subsequent evolution and eventual transformation into the cold, dry world we see today. The chemical composition of Mars, determined during its formation, would set the stage for all of its subsequent geological and atmospheric evolution. Mars is enriched in iron oxide, giving it its distinctive red color that has captivated human observers for millennia. This iron oxide, essentially rust, forms when iron-bearing minerals are exposed to oxygen, suggesting that Mars has experienced significant oxidation throughout its history. The interior structure of Mars, established during these early formation processes, consists of a core approximately 3,000 kilometers in diameter, surrounded by a mantle of silicate rock about 1,700 kilometers thick, and topped with a crust that varies in thickness from about 50 kilometers in the northern lowlands to over 100 kilometers in the southern highlands. This asymmetry between the northern and southern hemispheres, known as the Martian dichotomy, is one of the planet's most striking features and may have been established very early in its history. The formation of Mars was not an isolated event, but part of the broader story of planetary formation throughout the solar system. As Mars took shape, so too did its terrestrial companions, Mercury, Venus, and Earth. Each of these worlds followed a similar path of accretion and differentiation, yet each ended up remarkably different. Mars, with its intermediate size and distance from the Sun, would develop its own unique character, distinct from its planetary siblings. The final stages of Mars's formation involved a period called the Late Heavy Bombardment, which occurred approximately 3.9 billion years ago. During this time, the inner solar system was pelted with a barrage of asteroids and comets, possibly triggered by a reorganization of the outer planet's orbits. Mars, with its thinner atmosphere and lower gravity than Earth, was particularly vulnerable to these impacts. The scars from this bombardment can still be seen today in the form of massive impact basins like Hellas Planitia, which stretches over 2,000 kilometers across. Following its tumultuous formation, Mars entered a period that scientists now call the Noachian Era, named after Noachis Terra, a heavily cratered region in the planet's southern highlands. This era, spanning from approximately 4.1 to 3.7 billion years ago, represents perhaps the most Earth-like period in Mars's history, a time when liquid water flowed freely across its surface, carving valleys, filling crater lakes, and possibly even forming vast oceans. The evidence for water on ancient Mars is written across the planet's surface in a language of geology that spacecraft and rovers have been learning to read for decades. Dried riverbeds snake across the landscape, their branching patterns identical to those carved by rivers on Earth. These valley networks, particularly abundant in the southern highlands, tell us that water once flowed from high elevations to low, following the pull of gravity just as rivers do on our own planet. The atmosphere of Noachian Mars was dramatically different from the thin, cold envelope of gas that surrounds the planet today. To maintain liquid water on its surface, Mars needed a much thicker atmosphere, one capable of creating a greenhouse effect strong enough to warm the planet above the freezing point of water. This ancient atmosphere was likely composed primarily of carbon dioxide, with significant amounts of water vapor, nitrogen, and other gases. The atmospheric pressure may have been comparable to, or even greater than Earth's current sea level pressure. The source of this thick atmosphere was Mars's intense volcanic activity during the Noachian period. Massive volcanoes erupted across the planet, releasing enormous quantities of gas from the interior. These gases included water vapor, carbon dioxide, sulfur dioxide, and other compounds that contributed to both the atmosphere and the greenhouse effect. The volcanic activity was so intense that it resurfaced large portions of the planet, creating vast volcanic plains that we can still observe today. The climate of Noachian Mars remains one of the most debated topics in planetary science. While the geological evidence clearly indicates the presence of liquid water, maintaining warm enough temperatures for sustained liquid water presents a challenge. Mars receives only 43% of the sunlight that Earth receives, and the young sun was approximately 25% dimmer than it is today. This creates what scientists call the faint young sun paradox. How could Mars have been warm enough for liquid water when it received so little solar energy? Several theories have been proposed to solve this paradox. One possibility is that the greenhouse effect was enhanced by gases we haven't fully accounted for, such as methane or hydrogen. These gases are powerful greenhouse agents and could have provided the additional warming needed. Another theory suggests that Mars experienced periodic warming due to changes in its orbit and axial tilt, creating brief periods warm enough for liquid water to flow. Yet another possibility is that impacts from asteroids and comets periodically injected enough energy and greenhouse gases into the atmosphere to create temporary warm periods. The water on Noachian Mars didn't just flow in rivers, it accumulated in lakes and possibly oceans. Crater lakes were common, with water filling impact craters to form isolated bodies of water. Some of these crater lakes overflowed, carving outlet channels as the water spilled over the crater rim and flowed downslope. The sedimentary deposits left behind in these ancient lakebeds provide some of our best evidence for sustained liquid water on Mars. The possibility of an ancient Martian ocean is one of the most intriguing aspects of the planet's watery past. The northern lowlands of Mars, which lie several kilometers below the southern highlands, may once have been covered by a vast ocean. This hypothetical ocean, sometimes called Oceanus Borealis, would have covered approximately 1/3 of the planet's surface, comparable to the Atlantic Ocean on Earth. The evidence for this ocean includes what appear to be ancient shorelines, sedimentary deposits consistent with marine environments, and the distribution of valley networks that seem to have drained into the northern lowlands. If this ocean existed, it would have fundamentally altered Mars's climate system. Oceans act as massive heat reservoirs, moderating temperature extremes and driving weather patterns. An ocean on Mars would have created a hydrological cycle similar to Earth's, with evaporation from the ocean surface, cloud formation, precipitation, and runoff back to the ocean. This cycle would have been a powerful force for erosion and sediment transport, shaping the Martian landscape in ways we're still discovering. The chemistry of Mars's ancient water is another fascinating aspect of this story. By analyzing minerals formed in the presence of water, scientists have learned that Martian water varied considerably in its chemistry across different regions and time periods. Some areas show evidence of relatively fresh water, while others indicate highly acidic or salty conditions. This variation tells us that Mars had diverse aqueous environments, each with its own potential for supporting life. Clay minerals, which form in the presence of relatively neutral pH water, are abundant in Noachian-aged rocks. These clays, called phyllosilicates, require substantial amounts of water to form and indicate that water was not just present, but was interacting with rocks over extended periods. The widespread distribution of these clays suggests that water-rock interactions were common across much of Mars during the Noachian period. The role of groundwater in shaping Mars's surface cannot be overlooked. Much of Mars's water likely existed as groundwater, flowing through the porous rocks of the crust. This groundwater would have emerged at the surface in springs, contributing to the flow of rivers and the filling of lakes. Groundwater sapping, where flowing groundwater erodes overlying rock, appears to have been responsible for forming many of Mars's valley networks. These sapping valleys have characteristic features, including theater-shaped heads and relatively constant widths, that distinguish them from valleys carved by surface runoff. Hydrothermal systems, where hot water circulates through rocks, were likely common on Noachian Mars. The combination of volcanic heat and abundant water would have created ideal conditions for hydrothermal activity. These systems are particularly interesting from an astrobiological perspective, as similar environments on Earth host diverse communities of microorganisms. Evidence for ancient hydrothermal systems on Mars includes mineral assemblages that form only in hot water, and the remnants of what may have been hot springs. The interaction between water and Mars's cryosphere, its frozen water reservoirs, added another layer of complexity to the planet's hydrological system. Even during the Noachian period, the polar regions and high elevations would have been cold enough for water ice to be stable. This ice would have acted as a reservoir, storing water during cold periods and releasing it during warmer times. The boundary between liquid water and ice, called the cryosphere boundary, would have shifted with changes in climate, creating a dynamic system of freezing and thawing. Catastrophic floods represent some of the most dramatic water-related events in Mars's history. While many of these floods occurred after the Noachian period, some may have begun during this early era. These floods, possibly triggered by volcanic activity melting subsurface ice, or by the catastrophic release of water from pressurized aquifers, carved enormous channels across the Martian surface. The scale of these floods is difficult to comprehend. Some released volumes of water equivalent to all of Earth's oceans in a matter of weeks or months. The seasonal cycles on Noachian Mars would have created a dynamic and ever-changing landscape. If Mars had a thick atmosphere and liquid water, it would have experienced weather patterns including rainstorms, snow, and fog. The planet's axial tilt, similar to Earth's, would have created seasons with warmer summers and colder winters. These seasonal changes would have driven variations in river flow, lake levels, and ice coverage, creating a constantly evolving hydrological system. The biological potential of Noachian Mars is perhaps the most tantalizing aspect of this ancient ocean world. With liquid water, a thick atmosphere, and diverse chemical environments, Mars had many of the ingredients necessary for life as we know it. If life ever existed on Mars, the Noachian period would have been the most favorable time for its emergence and proliferation. The search for evidence of ancient Martian life focuses heavily on rocks and minerals from this era. Deltas, where rivers deposited sediment as they entered standing bodies of water, are among the most promising targets in the search for ancient life on Mars. These environments on Earth are rich in organic material and often preserve fossils. Several well-preserved deltas have been identified on Mars, including the spectacular delta in Jezero crater, which is currently being explored by NASA's Perseverance rover. The layered sediments in these deltas contain a record of ancient environmental conditions and may preserve evidence of past life. The duration of the warm, wet conditions on Noachian Mars remains uncertain. Some scientists argue for sustained warmth lasting hundreds of millions of years, while others favor a model of brief, episodic warm periods separated by long cold intervals. The geological evidence can be interpreted to support either scenario, and the truth may lie somewhere in between. What is clear is that liquid water was present on Mars's surface for geologically significant periods, long enough to carve valleys, fill lakes, and potentially support the emergence of life. The transition from the wet Noachian period to the drier conditions that followed was gradual rather than abrupt. As we'll explore in the next section, Mars began losing its atmosphere to space, and with it, the ability to maintain liquid water on its surface. But the Noachian period left an indelible mark on Mars, creating a landscape that still bears witness to a time when the red planet was blue with water. The minerals formed during the Noachian period provide a chemical record of ancient Mars that we're still learning to read. Different minerals form under different conditions of temperature, pressure, pH, and water availability. By mapping the distribution of these minerals across Mars's surface, scientists can reconstruct ancient environmental conditions and understand how they varied across the planet. This mineralogical record reveals a complex and varied ancient Mars, with different regions experiencing different conditions at the same time. The transformation of Mars from a warm, wet world to the cold, dry planet we see today represents one of the most dramatic planetary changes in our solar system's history. This metamorphosis didn't happen overnight, but unfolded over hundreds of millions of years, driven by a combination of factors that ultimately stripped Mars of its protective atmosphere and surface water. Understanding this transformation helps us appreciate not only Mars's past, but also the delicate balance that maintains habitability on rocky planets. The loss of Mars's magnetic field stands as perhaps the most crucial turning point in the planet's history. Sometime around 4 billion years ago, the dynamo that generated Mars's global magnetic field ceased to operate. The exact cause of this shutdown remains one of the great mysteries of planetary science, but its consequences were catastrophic. Without a magnetic field to deflect charged particles from the sun, Mars's atmosphere became vulnerable to erosion by the solar wind. The solar wind, a stream of charged particles flowing from the sun at speeds of hundreds of kilometers per second, constantly bombards all planets in our solar system. On Earth, our magnetic field channels these particles around the planet, protecting our atmosphere. But on Mars, once the magnetic field disappeared, the solar wind began directly interacting with the upper atmosphere, gradually stripping away gas molecules and sending them spiraling into space. This process, called atmospheric sputtering, works like a cosmic sandblaster. High-energy particles from the solar wind collide with molecules in Mars's upper atmosphere, transferring enough energy to knock them free of the planet's gravitational pull. Over millions of years, this process removed a significant portion of Mars's atmosphere, particularly the lighter elements like hydrogen. The loss of hydrogen, which comes from the breakdown of water molecules, meant that Mars was literally losing its water to space. The rate of atmospheric loss wasn't constant, but varied with solar activity. During solar storms, when the sun releases massive bursts of charged particles, the rate of atmospheric erosion increases dramatically. Early in the solar system's history, the sun was more active than it is today, producing more frequent and intense solar storms. This heightened activity would have accelerated the loss of Mars's atmosphere during the critical period following the shutdown of its magnetic field. Mars's small size played a crucial role in its atmospheric evolution. With only about 38% of Earth's surface gravity, Mars has a weaker grip on its atmosphere. Gas molecules moving at the same speed that would be retained by Earth's gravity can escape from Mars. This lower escape velocity means that Mars naturally loses atmosphere more readily than larger planets, even without the added pressure from solar wind erosion. The cooling of Mars's interior contributed to the planet's transformation in multiple ways. As the interior cooled, volcanic activity decreased, reducing the rate at which new gases were added to the atmosphere. On Earth, volcanoes continuously replenish atmospheric gases lost to various processes, maintaining a balance. But on Mars, as volcanism waned, the planet lost its ability to replace the atmosphere being stripped away by the solar wind. The formation of carbonate minerals in Mars's crust acted as another atmospheric sink. Carbon dioxide from the atmosphere reacted with water and rocks to form carbonates, locking the gas away in solid form. On Earth, plate tectonics recycles these carbonates back into the atmosphere through volcanic activity. But Mars lacks plate tectonics. Once carbon dioxide was locked into carbonate rocks on Mars, it was effectively removed from the atmosphere permanently. Impact erosion provided yet another mechanism for atmospheric loss. Large asteroid impacts, particularly common during the late heavy bombardment period, could blast portions of the atmosphere directly into space. These impacts were especially effective at removing atmosphere because they accelerated gas molecules to speeds exceeding Mars's escape velocity. Computer simulations suggest that a single large impact could remove a significant fraction of Mars's atmosphere, and Mars experienced many such impacts throughout its history. The photochemical breakdown of water vapor in Mars's upper atmosphere contributed to both water and atmospheric loss. Ultraviolet radiation from the sun breaks water molecules into hydrogen and oxygen. The light hydrogen atoms easily escape to space, while the heavier oxygen atoms remain behind. This process not only depleted Mars's water, but also altered the chemistry of its atmosphere, contributing to the oxidizing conditions that give Mars its red color today. As Mars's atmosphere thinned, a runaway feedback process began. A thinner atmosphere meant less greenhouse warming, leading to colder temperatures. Colder temperatures caused more water vapor to freeze out of the atmosphere, further reducing the greenhouse effect. This positive feedback loop accelerated the planet's cooling and drying, transforming Mars from a potentially habitable world to an increasingly hostile environment. The changing atmospheric pressure had profound effects on the stability of liquid water. As atmospheric pressure dropped below 6 millibars, the triple point of water, liquid water could no longer exist stably on most of Mars's surface. Below this pressure, water transitions directly from ice to vapor without passing through a liquid phase, a process called sublimation. This pressure threshold marked a critical point in Mars's transformation, effectively ending the era of flowing rivers and standing lakes. The collapse of Mars's hydrological cycle followed inevitably from the loss of atmospheric pressure. Without stable liquid water on the surface, the cycle of evaporation, precipitation, and runoff that had shaped Mars's landscape came to an end. Water became trapped as ice in the polar caps and subsurface, emerging only occasionally during rare warming events or volcanic eruptions. The once flowing rivers froze solid or evaporated, leaving behind only their dried channels as testament to wetter times. The oxidation of Mars's surface, which gives the planet its distinctive rusty red appearance, accelerated as the atmosphere evolved. The breakdown of water molecules released oxygen, which reacted with iron-bearing minerals in the soil and rocks. This oxidation process created the iron oxide minerals that dominate Mars's surface today. The red color that gives Mars its nickname is thus a direct result of its atmospheric evolution and the loss of its water. Climate models suggest that Mars's transformation wasn't necessarily smooth or monotonic. The planet may have experienced periods of temporary warming and thickening of the atmosphere, perhaps triggered by large volcanic eruptions or changes in orbital parameters. These transient warm periods might have allowed liquid water to flow briefly on the surface, carving some of the younger channel features we observe. But these reprieves were temporary, and the overall trend was toward a colder, drier planet. The role of dust in Mars's atmospheric evolution deserves special consideration. As Mars dried out, dust storms became increasingly common and intense. These storms can engulf the entire planet, lasting for months. While dust in the atmosphere can provide some greenhouse warming, it also increases the rate of atmospheric loss by expanding the upper atmosphere, making it more vulnerable to solar wind stripping. The prevalence of dust storms on modern Mars is both a consequence and a continuing cause of its thin atmosphere. The preservation of Mars's transformation in its geology provides us with a record of this dramatic change. Different regions of Mars preserve rocks from different time periods, allowing scientists to piece together the timeline of atmospheric loss. The transition from clay minerals, which form in neutral water, to sulfate minerals, which form in acidic conditions, marks a major shift in Mars's surface chemistry that corresponds to its atmospheric evolution. Isotopic evidence provides crucial insights into atmospheric loss processes. Mars's atmosphere is enriched in heavy isotopes of various elements compared to lighter isotopes. This enrichment occurs because lighter isotopes escape to space more readily than heavier ones. By measuring these isotopic ratios, scientists can estimate how much atmosphere Mars has lost over its history. Current estimates suggest Mars has lost between 60 and 90% of its original atmosphere. The polar caps of Mars serve as partial repositories of its lost atmosphere. These caps contain both water ice and frozen carbon dioxide, representing atmosphere that has been cold-trapped at the poles. The seasonal growth and shrinkage of these caps causes measurable changes in atmospheric pressure, demonstrating that even today, Mars's atmosphere continues to evolve through exchanges with surface reservoirs. The subsurface of Mars likely contains vast quantities of water ice, and possibly liquid water in deep aquifers. This subsurface water represents another reservoir of Mars's ancient atmosphere and hydrosphere. The presence of recurring slope lineae, dark streaks that appear seasonally on some Martian slopes, suggests that liquid water may still occasionally reach the surface, though this remains controversial among scientists. After the dramatic atmospheric loss that ended Mars's warm and wet period, the red planet entered an epoch of profound isolation and gradual change that would span billions of years. This vast stretch of time, from roughly 3.5 billion years ago to the present, encompasses most of Mars's history. During these eons, Mars evolved from a dying ocean world into the frozen desert we observe today. Yet this transformation was neither simple nor uniform, marked instead by periods of volcanic resurgence, episodic climate changes, and the slow but relentless sculpting of its surface by wind and ice. The Hesperian period, beginning approximately 3.7 billion years ago and lasting until about 3.2 billion years ago, marked the first major epoch following Mars's Great Drying. Named after Hesperia Planum, a moderately cratered region in Mars's southern hemisphere, this era witnessed the last gasps of widespread water activity on the planet's surface. While the rivers of the Noachian had largely ceased flowing, the Hesperian saw catastrophic floods of unprecedented scale, as if Mars was releasing its remaining water in violent, sporadic bursts. These outburst floods carved the enormous outflow channels that remain among Mars's most spectacular features. Channels like Cassae Valles, stretching over 3,000 kilometers, and Ares Vallis, where NASA's Pathfinder mission landed, speak to floods that dwarfed anything in Earth's history. The water for these floods likely came from vast underground reservoirs, suddenly released when volcanic heat melted permafrost, or when the pressure in confined aquifers exceeded the strength of overlying rock. The scale of these floods is difficult to comprehend. Some carried water volumes exceeding 1 million cubic meters per second, enough to drain Earth's Mediterranean Sea in mere months. Volcanic activity during the Hesperian period reshaped vast regions of Mars. The great volcanic province of Tharsis continued to grow, eventually forming a bulge in Mars's crust that rises 10 kilometers above the surrounding plains and spans 5,000 kilometers across. This massive accumulation of volcanic rock actually shifted Mars's rotation axis, causing the entire planet to reorient itself to accommodate the new mass distribution. The formation of Tharsis had global consequences, creating a network of cracks and valleys that radiate from its center like spokes on a wheel, including the vast Valles Marineris canyon system. Olympus Mons, the tallest volcano in our solar system, reached much of its current height during this period. Standing 21 kilometers tall, nearly 3 times the height of Mount Everest, and spanning 600 kilometers across, Olympus Mons is a shield volcano of staggering proportions. Its formation required millions of years of repeated eruptions, each adding layers of basaltic lava to the growing edifice. The volcano's immense size is partly due to Mars's lack of plate tectonics. Without moving plates to carry the volcano away from its magma source, it could continue growing in the same location for billions of years. The Amazonian period, beginning around 3.2 billion years ago and continuing to the present day, encompasses the longest chapter in Mars's history. Named after Amazonas Planitia, a smooth plain with very few impact craters, this era is characterized by low rates of geological activity and the dominance of wind and ice in shaping the landscape. Yet even in this seemingly quiet period, Mars has experienced remarkable changes and occasional bursts of activity that remind us the planet is not entirely dead. Throughout these billions of years, Mars's climate underwent dramatic oscillations, driven by changes in its orbital parameters. The planet's axial tilt, or obliquity, varies chaotically over timescales of millions of years, swinging between 15 and 35 degrees. Currently at 25 degrees, similar to Earth's tilt, Mars has experienced periods when its axis was tilted much more dramatically. During high obliquity periods, the poles receive more direct sunlight, causing massive sublimation of the polar ice caps and temporarily thickening the atmosphere. These climate swings created alternating periods of ice ages and relative warmth, each lasting hundreds of thousands to millions of years. The polar layered deposits provide a remarkable record of these climate cycles. These deposits, composed of alternating layers of ice and dust, extend up to 3 kilometers thick at the North Pole and up to 4 kilometers at the South Pole. Each layer represents a different climate period, with dustier layers corresponding to times of global dust storms and cleaner ice layers representing calmer periods. Reading these layers is like reading tree rings, except each ring represents thousands of years of Martian history. The total volume of water ice in these polar deposits is enormous. If melted, it would cover the entire planet to a depth of approximately 20 meters. Wind has been the primary sculptor of Mars's surface throughout the Amazonian period. With an atmosphere too thin to support liquid water but thick enough to move dust and sand, wind erosion and deposition have created a variety of distinctive features. Vast dune fields, some covering areas larger than Texas, migrate slowly across the Martian surface. Yardangs, streamlined hills carved by wind erosion, point like arrows in the direction of prevailing winds. Dust devils, miniature tornadoes that can tower kilometers high, leave dark tracks across the landscape as they vacuum up the bright surface dust, revealing darker material beneath. The global dust storms that periodically engulf Mars represent one of the most dramatic ongoing phenomena on the planet. These storms typically begin in the southern hemisphere during southern summer, when Mars is closest to the sun. The increased solar heating creates strong winds that lift dust from the surface. Once airborne, the dust absorbs sunlight, heating the atmosphere and creating stronger winds that lift more dust in a feedback loop that can envelop the entire planet within weeks. These global storms can last for months, fundamentally altering the planet's appearance and climate during their duration. Beneath Mars's dusty surface lies a cryosphere of frozen water that extends globally. This subsurface ice, detected by orbital spacecraft and confirmed by landers, represents a vast reservoir of water. In some regions, particularly at high latitudes, water ice comprises more than 50% of the soil by volume. This ice occasionally becomes exposed through impact craters or erosion, revealing clean, white ice that gradually darkens as it accumulates dust. The presence of this extensive subsurface ice suggests that Mars's water wasn't entirely lost to space, but was instead locked away beneath the surface, waiting. The mystery of recurring slope lineae has captivated scientists studying modern Mars. These dark streaks appear seasonally on steep slopes, growing during warm seasons and fading during cold periods. Initially thought to be flowing briny water, recent studies suggest they might instead be dry avalanches of dust and sand. Yet the debate continues, and if liquid water is involved, even in small amounts, it would represent the only known active liquid water on Mars's surface today, a remarkable possibility on a planet we consider dry and dead. Impact cratering has continued throughout Mars's long solitude, though at a much reduced rate compared to the early solar system. Each impact tells a story, not just of the collision itself, but of Mars's response to it. Fresh craters expose subsurface ice, creating temporary atmospheres of water vapor that quickly freeze and sublime. Larger impacts can trigger landslides that reveal layered deposits, providing windows into Mars's geological history. The pattern of crater degradation also reveals information about erosion rates and climate conditions over billions of years. The geological processes operating during these 4 billion years were subtle but persistent. Seasonal frost cycles, where carbon dioxide and water ice condense and sublime, gradually break down rocks through repeated freezing and thawing. Chemical weathering, though slow in Mars's dry environment, has altered surface minerals over vast timescales. The interaction between the atmosphere and surface has created unique minerals found nowhere else in the solar system, each telling a story of Mars's particular chemical evolution. Mars's moons, Phobos and Deimos, have been silent companions throughout this long history. These small, irregular bodies, likely captured asteroids, orbit close to Mars and have been gradually spiraling inward and outward respectively due to tidal forces. Phobos, the larger and closer moon, is slowly approaching Mars and will either crash into the planet or break apart into a ring system in about 50 million years. These moons have witnessed Mars's entire transformation, their heavily cratered surfaces recording the same bombardment history as their parent planet. The interior of Mars has continued cooling throughout these billions of years, though volcanic activity hasn't entirely ceased. The youngest volcanic flows on Mars appear to be only a few million years old, yesterday in geological terms. These recent eruptions suggest that Mars retains some internal heat and could potentially experience future volcanic activity. The detection of methane in Mars's atmosphere, which shouldn't persist for long given the planet's chemistry, hints at possible ongoing geological or even biological processes deep beneath the surface. Marsquakes, detected by NASA's InSight lander, reveal that Mars remains seismically active. These quakes, while generally smaller than earthquakes, demonstrate that Mars's interior is still cooling and contracting, causing the crust to crack and shift. The patterns of seismic waves traveling through Mars have allowed scientists to probe the planet's internal structure, revealing details about its core, mantle, and crust that were previously unknown. The long-term evolution of Mars's orbit has played a crucial role in its climate history. Mars's orbital eccentricity varies cyclically, sometimes bringing it much closer to the Sun at certain points in its orbit. These variations, combined with the obliquity cycles, create complex climate patterns that have repeatedly reorganized the distribution of ice and dust on the planet. During some periods, conditions might have briefly allowed liquid water to exist at certain locations, creating temporary oases in an otherwise frozen world. The preservation of ancient terrains on Mars provides a unique window into the early solar system. Unlike Earth, where plate tectonics and erosion have erased most ancient surfaces, Mars preserves rocks dating back over 4 billion years. These ancient terrains contain information about conditions in the early solar system that has been lost on other worlds. In this sense, Mars serves as a museum of planetary evolution, preserving exhibits from epochs long vanished elsewhere. The interaction between dust and ice has created unique features found nowhere else. Dust-ice mixtures behave differently than pure ice or dust alone, flowing like glaciers under certain conditions. These dust-ice flows have carved distinctive patterns on crater walls and canyon slopes, creating features that puzzled scientists until they understood the unique rheology of these mixed materials. The Swiss cheese terrain at the South Pole, where carbon dioxide ice sublimates in circular patterns, represents another uniquely Martian phenomenon. Throughout these eons of solitude, Mars has been slowly losing mass to space. Not just atmospheric gases, but also dust particles can be accelerated to escape velocity during global dust storms. This gradual loss of material, while tiny compared to the planet's total mass, represents a continuous bleeding of Mars into interplanetary space. Some of this material eventually reaches Earth as Martian meteorites, providing us with actual samples of the red planet. The chemical evolution of Mars's surface during the Amazonian has produced a variety of secondary minerals. Perchlorates, highly oxidizing salts discovered by the Phoenix lander, appear to be widespread in Martian soil. These salts, which can lower the freezing point of water dramatically, might allow briny water to exist temporarily under current Martian conditions. Their presence also poses challenges for future human exploration, as perchlorates are toxic to humans and corrosive to equipment. The gradual redistribution of volatiles on Mars has created distinct latitude-dependent features. Ground ice is stable at high latitudes, but sublimates at low latitudes, creating a variety of thermokarst features similar to those found in Earth's permafrost regions. Polygonal terrain, created by repeated freezing and thawing cycles, covers vast areas of Mars's high latitudes. These polygons, ranging from meters to tens of meters across, create geometric patterns visible from orbit that speak to ongoing freeze-thaw processes. Long before telescopes revealed Mars as a world, before spacecraft visited its russet plains, and before rovers traced their tracks through its ancient dust, human beings looked up at a wandering red star and wondered. Mars, visible to the naked eye as a distinctly reddish point of light that moves against the background of fixed stars, has captivated human imagination since prehistoric times. The story of humanity's relationship with Mars begins not with science, but with mythology, astrology, and the deep human need to find meaning in the patterns of the night sky. The earliest known observations of Mars date back to ancient Egypt, where astronomers carefully tracked the red planet's motion across the sky. The Egyptians called Mars Horus the Red, or Her-Desher, meaning the Red One, and associated it with destruction and backwards motion due to its retrograde loops through the sky. Egyptian astronomers were sophisticated enough to recognize that Mars followed a pattern, appearing in the same position relative to the stars approximately every 780 days, a cycle we now know as Mars's synodic period. In ancient Mesopotamia, the cradle of astronomy, Babylonian astronomers created detailed records of Mars's position that spanned centuries. These cuneiform tablets, some dating back 3,000 years, contain mathematical tables predicting Mars's future positions with remarkable accuracy. The Babylonians called Mars Nergal, after their god of war, plague, and destruction, establishing an association between the red planet and conflict that would persist across cultures. Their observations were so precise that modern astronomers can use them to study long-term changes in planetary orbits. The ancient Chinese astronomers, working independently from their Western counterparts, developed their own sophisticated understanding of Mars. They called it Yinghuo, meaning fire star or sparkling diluter, referring both to its red color and its confusing retrograde motion. Chinese astronomical records, some extending back over 4,000 years, provide continuous observations of Mars that include detailed descriptions of its brightness variations and close approaches to other planets. These records are so complete that they've helped modern scientists study historical changes in Mars's orbit and rotation. In ancient India, Mars held a prominent place in both astronomy and astrology. Known as Mangala or Angaraka in Sanskrit, Mars was personified as a red-bodied god born from the sweat of Shiva. Indian astronomers calculated Mars's orbital period with impressive accuracy and developed mathematical models to predict its position. The Surya Siddhanta, an ancient Indian astronomical text, contains calculations of Mars's diameter and distance from Earth that, while not accurate by modern standards, demonstrate sophisticated mathematical thinking about planetary dimensions. The Greeks inherited and expanded upon earlier astronomical traditions, transforming observations into geometric models. They called Mars Ares after their god of war, cementing the martial association that would give the planet its modern name. Greek astronomers grappled with explaining Mars's retrograde motion, the apparent backwards movement of the planet against the stars that occurs when Earth overtakes Mars in its orbit. This puzzling phenomenon would drive astronomical thinking for centuries, ultimately contributing to the revolutionary realization that Earth itself moves through space. Aristotle's geocentric model, which placed Earth at the center of the universe, struggled to explain Mars's behavior. The planet's dramatic brightness variations, becoming over 20 times brighter at closest approach than at its faintest, challenged the Greek notion of perfect, unchanging celestial spheres. Ptolemy's solution, developed in the 2nd century CE, involved a complex system of circles upon circles called epicycles. While wrong in its fundamental assumptions, this model could predict Mars's position accurately enough for practical purposes, and remained the standard for over 1,000 years. The Romans, inheriting Greek astronomical knowledge, gave Mars the name we use today, after their god of war. But Mars meant more to Rome than just a deity. He was the father of Romulus and Remus, the legendary founders of Rome, making the red planet symbolically connected to the very origins of Roman civilization. Roman farmers also associated Mars with agricultural protection, celebrating festivals in his honor to ensure good harvests, showing that even in antiquity, humanity's relationship with Mars extended beyond war to encompass life and growth. In the Americas, indigenous civilizations developed their own rich traditions around Mars. The Maya, accomplished astronomers who created sophisticated calendars, carefully tracked Mars's movements and incorporated them into their complex astronomical tables. They associated Mars with war and used its position to time military campaigns. The Dresden Codex, one of only 4 surviving Maya books, contains tables that track Mars's motion with such precision that they can predict its position accurately over periods of hundreds of years. The Inca called Mars Ocayok, associating it with llamas and agricultural cycles rather than war. They observed that Mars's brightness varied dramatically, and used these observations to predict weather patterns and plan agricultural activities. The red planet's appearance at certain times of year signaled when to plant or harvest specific crops, integrating Mars into the practical rhythms of Andean life. Islamic astronomers during the Golden Age made crucial contributions to our understanding of Mars. They called it Mirik, or Al-Kahir, and their observations refined the orbital parameters calculated by earlier Greek astronomers. Al-Battani, working in the 9th century, made observations of Mars that improved upon Ptolemy's measurements. Ibn al-Haytham, in the 11th century, attempted to measure the distance to Mars using parallax, pioneering techniques that would later revolutionize astronomy. The Aboriginal Australians, whose astronomical traditions stretch back tens of thousands of years, incorporated Mars into their Dreamtime stories. Different groups had various names and stories for Mars, often relating to hawks, eagles, or other red-colored animals. The Wardaman people called Mars Bilyara, associating it with eagles and using its position to predict when certain plants would fruit. These oral traditions preserved astronomical knowledge across countless generations without written records. Medieval European observations of Mars were often clouded by astrological interpretations, yet careful observers continued to track its motion. The Great Conjunction of Jupiter and Mars in 1385 was widely observed and interpreted as an omen. Astronomers of this period noticed that Mars's retrograde loops varied in size and shape, a phenomenon that the epicycle model struggled to explain fully. These accumulating discrepancies would eventually contribute to the model's downfall. The Norse peoples associated Mars with their god Tyr, a deity of war and justice. Viking navigators may have used Mars, along with other planets and stars, for navigation during their long sea voyages. The red planet appears in several Norse sagas, often as an omen of coming conflict or change. The connection between Mars's color and blood appears consistently across Norse literature, showing how the planet's distinctive appearance shaped cultural interpretations. In Japan, Mars was known as Kase, meaning fire star, and was associated with the element of fire in Chinese-influenced cosmology. Japanese astronomers, particularly during the Edo period, made detailed observations of Mars and other planets, creating star maps that blend scientific observation with artistic beauty. The appearance of Mars in certain configurations was thought to influence earthly events, from natural disasters to political changes. The Aztecs called Mars Huitzilopochtli's star, after their god of war and the sun. They believed that Mars's red color came from the blood of sacrificed warriors, and that the planet's movements influenced the outcome of battles. Aztec priests carefully tracked Mars's position, using it to determine auspicious times for warfare and religious ceremonies. The planet's retrograde motion was interpreted as the god turning back to survey the battlefield. Persian astronomers, working at the crossroads of Eastern and Western traditions, made significant contributions to Mars observation. They refined calculations of Mars's orbit and developed new instruments for measuring planetary positions. The Zigi-Ilkhani, compiled in the 13th century at the Maragay Observatory, contained highly accurate tables of Mars's motion that improved upon all previous work. The astrological significance of Mars persisted across cultures, with the planet universally associated with energy, conflict, and transformation. Even cultures that had no contact with each other independently associated Mars with similar themes, suggesting that the planet's red color and unusual motion naturally evoked certain human responses. This cross-cultural consistency speaks to something fundamental about how humans interpret celestial phenomena. The transition from mythological to scientific understanding of Mars was gradual and uneven across cultures. Even as telescopes began revealing Mars as a world rather than just a wandering star, cultural and astrological associations persisted. The red planet remained a symbol of war in literature and popular culture, long after astronomers understood it as a planet similar to Earth. This dual nature of Mars, as both a scientific object of study and a cultural symbol, continues to this day. The invention of the telescope in the early 17th century marked a watershed moment in humanity's understanding of Mars, transforming it from a wandering red star into a world with observable features, seasons, and mysteries that would captivate scientists for centuries to come. This revolutionary instrument allowed humans, for the first time, to see Mars as more than just a point of light, revealing it as a sphere with surface markings that changed over time, polar ice caps that waxed and waned with the seasons, and an appearance that suggested it might be a world not entirely unlike our own. Galileo Galilei, the first person known to observe Mars through a telescope, turned his modest instrument toward the red planet in 1609. Though his telescope was primitive by modern standards, providing only about 20 times magnification, Galileo could discern that Mars appeared as a disk rather than a point of light. He noted that Mars seemed to change in apparent size over time, correctly interpreting this as evidence that Mars's distance from Earth varied. In a letter dated December 30, 1610, Galileo wrote that he could not discern any features on Mars's surface, but the mere fact that it showed a disk was revolutionary. The first person to record surface features on Mars was Francisco Fontana, a Neapolitan lawyer and amateur astronomer. In 1636, Fontana made a drawing of Mars that showed a dark spot on its surface, though modern astronomers debate whether this was a real feature or an optical artifact of his primitive telescope. Fontana's drawing, crude as it was, represented humanity's first attempt to map another planet's surface, the beginning of Martian cartography. Christian Huygens, the Dutch astronomer and mathematician, made the first unambiguous observation of a surface feature on Mars. On November 28, 1659, Huygens sketched a distinctive dark marking on Mars that modern astronomers recognize as Syrtis Major, a vast dark region that remains one of Mars's most prominent features. Huygens used his observations to make another groundbreaking discovery. By watching this feature rotate across Mars's disk, he determined that Mars rotates on its axis once every 24 hours, remarkably close to Earth's rotation period. Giovanni Domenico Cassini, working at the Paris Observatory, expanded upon Huygens' work with a series of detailed observations in 1666. Cassini confirmed Mars's rotation period, refining it to 24 hours and 40 minutes, only 3 minutes off from the modern value. He also made the first observations of Mars's polar ice caps, noting white spots at the planet's poles that seemed to change in size. Cassini's careful observations over multiple oppositions allowed him to track long-term changes on Mars's surface. The quality of telescopic observations improved dramatically throughout the 18th century as lens-making techniques advanced. William Herschel, the discoverer of Uranus, made extensive observations of Mars between 1777 and 1783. Herschel was the first to propose that Mars's polar caps were made of ice or snow, analogous to Earth's polar regions. He observed that the southern polar cap nearly disappeared during Mars's southern summer, while the northern cap shrank but never vanished completely. From these observations, Herschel correctly deduced that Mars experiences seasons similar to Earth's. Herschel made another crucial observation. Mars's axis of rotation is tilted relative to its orbital plane. He measured this tilt, or obliquity, as approximately 24 degrees, remarkably close to the modern value of 25 degrees, and similar to Earth's tilt of 23.5 degrees. This similarity suggested that Mars experiences seasons much like Earth's, with each hemisphere experiencing summer when tilted toward the sun and winter when tilted away. The atmosphere of Mars became a subject of serious scientific inquiry during this period. Herschel claimed to have observed clouds on Mars, though distinguishing between atmospheric phenomena and surface features proved challenging with the telescopes of his era. Honoré Flaugergues, observing Mars during the favorable opposition of 1809, noted yellow clouds that appeared to obscure surface features, likely the first definitive observations of Martian dust storms. Johann Hieronymus Schröter, a German astronomer working in the late 18th and early 19th centuries, made detailed observations of Mars over many years. While some of his claims, such as seeing mountains on Mars 20 kilometers tall, were products of optical illusions and wishful thinking, his systematic approach to planetary observation established methodologies that future astronomers would refine. Schröter was among the first to attempt to measure the Martian day precisely and to create detailed maps of the planet's surface features. The early 19th century saw increasingly sophisticated attempts to map Mars's surface. Wilhelm Beer and Johann von Madler, working at Beer's private observatory in Berlin, created the first reasonably accurate map of Mars in 1840. Their map, based on observations made between 1828 and 1830, established a system of nomenclature for Martian features and served as a reference point for future observers. They also made precise measurements of Mars's rotation period, determining it to be 24 hours, 37 minutes, and 22.7 seconds, accurate to within a tenth of a second. The development of better telescopes and observing techniques in the mid-19th century revealed Mars in unprecedented detail. Angelo Secchi, an Italian Jesuit priest and astronomer, made detailed color observations of Mars, noting that different regions appeared to have different hues. He described some areas as reddish-yellow, others as greenish or blue-gray. Secchi was also among the first to suggest that the color changes observed on Mars might be due to seasonal vegetation, an idea that would dominate Martian studies for decades. Richard Proctor, an English astronomer, created detailed maps of Mars in 1867, based on drawings by William Rutter Dawes. Proctor's maps were the first to use a systematic nomenclature system, naming features after astronomers who had studied Mars. Though his naming system would later be replaced, Proctor's maps represented a significant advance in Martian cartography and helped establish the idea that Mars's features were permanent enough to be mapped reliably. The opposition of 1877 proved to be a turning point in Mars observation. Oppositions occur approximately every 26 months when Earth passes between Mars and the Sun, bringing the two planets relatively close together. The 1877 opposition was particularly favorable, with Mars approaching within 56 million kilometers of Earth. Astronomers worldwide prepared for this event with improved telescopes and new observing techniques. Asaph Hall, working at the United States Naval Observatory in Washington, made a stunning discovery during the 1877 opposition. Mars has 2 small moons. On August 12th, he discovered Deimos, the outer moon, and on August 18th, Phobos, the inner moon. These discoveries were remarkable not just for revealing Mars's satellites, but for demonstrating the power of improved telescopes and careful observation. The moons were named after the Greek gods of fear and panic, the attendants of Ares, the Greek equivalent of Mars. Nathaniel Green, an English artist and amateur astronomer, created some of the most accurate pre-photographic maps of Mars during the 1877 opposition. Green's artistic training allowed him to capture subtle details that other observers missed, and his maps showed a Mars covered with complex, interconnected dark markings. Green was skeptical of the idea that these markings represented seas or vegetation, presciently suggesting they might be geological features instead. The introduction of spectroscopy to planetary astronomy in the late 19th century opened new windows into Mars's nature. William Huggins, a pioneer of astronomical spectroscopy, attempted to detect water vapor in Mars's atmosphere by comparing the spectrum of Mars with that of the Moon. While his instruments weren't sensitive enough to detect the trace amounts of water vapor actually present, his work established spectroscopy as a crucial tool for planetary investigation. Photography began to supplement visual observation in the late 19th century, though early photographic plates were not sensitive enough to capture fine detail on Mars. The first successful photographs of Mars were taken in 1890, but they showed less detail than skilled visual observers could see. It would be decades before photography surpassed the human eye for planetary observation. But these early efforts laid the groundwork for future advances. The question of Mars's atmosphere composition and density became increasingly important as observations improved. Some astronomers claimed to see clouds and atmospheric phenomena, while others argued that Mars's atmosphere must be extremely thin based on the sharpness of surface features. Spectroscopic observations attempted to detect oxygen and water vapor, with conflicting results that wouldn't be fully resolved until the space age. No chapter in the history of Mars observation has captured the public imagination quite like the Great Canal controversy that dominated the late 19th and early 20th centuries. This extraordinary episode, which saw respected astronomers claiming to observe vast networks of artificial waterways on Mars, transformed the red planet from a subject of purely scientific interest into a cultural phenomenon that influenced literature, philosophy, and humanity's conception of its place in the universe. The controversy began with Giovanni Virginio Schiaparelli, director of the Brera Observatory in Milan, during the favorable opposition of 1877. Using a relatively modest 22-centimeter telescope, Schiaparelli observed what appeared to be a network of linear features crossing Mars's surface. He called these features canali, an Italian word that can mean either natural channels or artificial canals. This linguistic ambiguity would have profound consequences when his work was translated into English, with many choosing the more sensational interpretation of artificial canals. Schiaparelli's maps showed Mars covered with a geometric network of straight lines connecting darker regions he called seas or oases. These canali appeared to be perfectly straight, sometimes extending for thousands of kilometers across the planet's surface. Some appeared as single lines, while others seemed to be doubled, running in parallel pairs. Schiaparelli meticulously catalogued these features, giving them names drawn from classical mythology and geography: Ganges, Euphrates, Nilus, and dozens of others. The astronomical community initially received Schiaparelli's observations with skepticism. Many experienced observers, using telescopes as powerful or more powerful than Schiaparelli's, could not see the canali. However, Schiaparelli's reputation as a careful observer, combined with the romantic appeal of his observations, gradually won converts. Some astronomers began reporting their own observations of canali, though rarely with the detail and consistency that Schiaparelli claimed. Percival Lowell, a wealthy American businessman turned astronomer, transformed the canal observations from a scientific curiosity into a theory of Martian civilization. In 1894, Lowell established an observatory in Flagstaff, Arizona, specifically to study Mars. The clear, steady air of the high desert location provided excellent viewing conditions, and Lowell threw himself into Mars observation with passionate intensity. Lowell not only confirmed Schiaparelli's canali, but elaborated them into an intricate network of over 500 canals. More significantly, he developed an elaborate theory to explain their existence. Mars, Lowell argued, was an ancient dying world whose inhabitants had constructed a planet-wide irrigation system to transport water from the polar ice caps to the equatorial deserts. The canals themselves, he claimed, were not visible directly. What observers saw were strips of irrigated vegetation along the canal banks. Through a series of popular books, Mars in 1895, Mars and Its Canals in 1906, and Mars as the Abode of Life in 1908, Lowell presented his vision of Martian civilization to the public. His writing was eloquent and persuasive, painting a picture of an advanced civilization struggling against planetary desiccation. The Martians, in Lowell's conception, had transcended war and nationalism to work together on a planetary scale, a lesson he suggested humanity would do well to learn. The public response to Lowell's ideas was extraordinary. Newspapers carried regular updates on Mars observations, and public lectures on the planet drew enormous crowds. The idea of Martian civilization influenced literature profoundly. Most notably, H.G. Wells' The War of the Worlds, published in 1898, which imagined Martians fleeing their dying world to invade Earth. Edgar Rice Burroughs' Barsoom series, beginning with A Princess of Mars in 1912, created an elaborate fantasy of Martian civilization directly inspired by Lowell's theories. The scientific community remained deeply divided. Many respected astronomers supported the canal observations, if not necessarily Lowell's interpretation of them. Camille Flammarion in France became an enthusiastic supporter of the canal theory, writing his own popular books about Mars. William Pickering, Lowell's assistant and later rival, claimed to observe not just canals but also oases that seemed to change with the seasons, which he interpreted as vegetation. However, skepticism remained strong among many astronomers. Edward Emerson Barnard, using the powerful telescopes at Lick Observatory, reported that he could not see distinct canals, but rather a complex mottling of the Martian surface. Barnard suggested that the canals might be an optical illusion created when the eye attempts to connect scattered dark markings. This explanation gained support from experiments showing that observers viewing random patterns of dots through telescopes would often report seeing connecting lines that didn't exist. Eugene Antoniadi, a Greek-French astronomer, delivered what many considered the death blow to the canal theory. During the exceptional opposition of 1909, Antoniadi used the 83-centimeter telescope at Meudon Observatory, one of the largest telescopes in Europe. Under excellent viewing conditions, Antoniadi observed that what appeared as lines at the limit of visibility resolved into complex patterns of irregular spots and shadings when seen clearly. He created detailed maps showing Mars's surface as a complex natural landscape rather than a geometric network of canals. The canal controversy revealed important truths about the psychology of observation and the influence of expectation on perception. Studies conducted during this period showed that observers who were told to expect canals were more likely to report seeing them, while those observing without preconceptions typically saw only irregular markings. This demonstrated the powerful role that cognitive bias plays in scientific observation, a lesson that remains relevant today. Photography gradually provided more objective evidence against the canals. As photographic techniques improved in the early 20th century, images of Mars consistently failed to show the geometric canal network. Defenders of the canal theory argued that photography couldn't capture the fine details visible to the trained eye during moments of steady atmospheric seeing. But the accumulation of photographic evidence gradually undermined support for the canals. Spectroscopic observations added another line of evidence against an inhabited Mars. Attempts to detect oxygen and water vapor in Mars's atmosphere produced increasingly discouraging results. By the 1920s, it was clear that Mars' atmosphere was much thinner than Earth's and contained little or no oxygen. This made the existence of advanced life on Mars increasingly implausible, though some continued to hold out hope for simple vegetation. The cultural impact of the canal controversy extended far beyond astronomy. The idea of Martian civilization influenced philosophical debates about humanity's uniqueness and destiny. Some saw in Lowell's vision of cooperative Martians a model for human society, while others used the supposed decline of Martian civilization as a warning about Earth's future. The controversy also sparked serious scientific discussion about the possibility of extraterrestrial life, helping establish astrobiology as a legitimate field of inquiry. Radio experiments added another dimension to the Martian fever. In 1924, when Mars made its closest approach to Earth in over a century, the United States Navy requested radio silence to listen for possible signals from Mars. Though no signals were detected, the experiment demonstrated how seriously the possibility of Martian intelligence was taken. Nikola Tesla and Guglielmo Marconi both claimed at various times to have detected radio signals that might have originated from Mars, though these claims were never substantiated. The canal controversy also influenced early thoughts about space exploration. As early as the 1890s, inspired by the possibility of Martian civilization, writers and scientists began seriously considering how humans might travel to Mars. Konstantin Tsiolkovsky in Russia and Robert Goddard in the United States, pioneers of rocketry, were both influenced by the idea of Mars as an inhabited world worth visiting. The dawn of the space age in the late 1950s transformed Mars from a distant object of telescopic observation into a destination for robotic explorers, ushering in an era of discovery that would systematically dismantle old myths while revealing truths far more extraordinary than anyone had imagined. The journey to reach Mars with spacecraft proved to be one of the most challenging endeavors in human history, with early missions suffering a failure rate that earned Mars a reputation as the spacecraft graveyard of the solar system. The Soviet Union, riding high on the success of Sputnik and eager to claim another space first, launched the earliest attempts to reach Mars. On October 10, 1960, the Soviets launched Marsnik 1, humanity's first attempt to send a spacecraft to Mars. The mission failed to reach Earth orbit when the third stage of its rocket malfunctioned, crashing back to Earth over Siberia. 4 days later, Marsnik 2 met a similar fate. These failures were kept secret for decades, known only through Western intelligence tracking of Soviet launches. The United States entered the Mars race in 1964 with Mariner 3, which launched on November 5 but failed when its protective shroud failed to separate, leaving the spacecraft trapped and unable to deploy its solar panels. The mission died in space, a costly failure that nearly ended NASA's Mars program before it began. However, just 3 weeks later, on November 28, 1964, Mariner 4 launched successfully, beginning a journey that would revolutionize our understanding of Mars. Mariner 4's voyage to Mars took 7.5 months, a journey of over 500 million kilometers through interplanetary space. During this time, mission controllers could only wait and hope that their spacecraft would survive the journey. The challenges were immense. Cosmic radiation, micrometeorite impacts, the extreme temperature variations of space, and the need to maintain precise navigation across vast distances with 1960s technology. On July 15, 1965, Mariner 4 flew within 9,800 kilometers of Mars, snapping 21 photographs as it passed. These images, each taking nearly 9 hours to transmit back to Earth, revealed a Mars that shocked the scientific community. Instead of a world with possible canals, vegetation, or signs of civilization, Mariner 4 showed a cratered, moon-like landscape. The atmosphere was measured at less than 1% of Earth's pressure, far too thin to support liquid water or complex life as we know it. The impact of Mariner 4's findings cannot be overstated. In 21 grainy photographs, decades of speculation about Martian civilization were swept away. The images showed ancient impact craters, some over 100 kilometers across, indicating that Mars's surface was billions of years old and geologically inactive. The thin atmosphere meant that Mars was a frozen desert, with temperatures measured at -100 degrees Celsius at the South Polar Cap. The Soviet Union continued its attempts to reach Mars throughout the 1960s, but success remained elusive. Mars 1, launched in November 1962, lost contact with Earth after traveling 100 million kilometers. Zond 2, launched in 1964, suffered a similar fate. The Soviets' ambitious Mars 1969A and 1969B missions, intended to be orbiters, Both failed during launch. These failures highlighted the extraordinary difficulty of interplanetary spaceflight, where a single component failure could doom an entire mission. NASA's Mariner 6 and 7, launched in early 1969, built upon Mariner 4's success with more sophisticated instruments and cameras. Flying by Mars in July and August 1969, just days after Apollo 11's moon landing, these spacecraft returned 200 images that covered about 20% of Mars's surface. They confirmed Mariner 4's findings of a cratered desert world, but also revealed new types of terrain, including chaotic terrain and the polar ice cap's layered deposits. The year 1971 marked a turning point in Mars exploration. NASA's Mariner 9 and two Soviet spacecraft, Mars 2 and Mars 3, all arrived at Mars within weeks of each other in November and December. However, they found Mars engulfed in a global dust storm, the largest ever observed, with winds reaching hundreds of kilometers per hour and dust clouds reaching 70 kilometers into the atmosphere. The planet was completely obscured, appearing as a featureless orange ball. Mars 2 and Mars 3 each carried both an orbiter and a lander. Mars 2's lander became the first human-made object to reach Mars's surface on November 27, 1971, though it crashed rather than landed softly. Mars 3's lander achieved the first successful soft landing on December 2, 1971, and transmitted for 20 seconds before falling silent, possibly damaged by the intense dust storm. These 20 seconds marked humanity's first successful transmission from the Martian surface, a triumph despite its brevity. Mariner 9, programmed to wait for the dust storm to clear, became the first spacecraft to orbit another planet. As the dust settled over the following weeks, Mariner 9 revealed a Mars far more complex and geologically diverse than anyone had imagined. The spacecraft discovered Olympus Mons, the solar system's largest volcano, and the Valles Marineris canyon system, stretching over 4,000 kilometers. It found ancient river valleys, suggesting that liquid water once flowed on Mars, reigniting interest in the possibility of past Martian life. Over its operational lifetime, Mariner 9 mapped 85% of Mars's surface, returning over 7,000 images. It discovered that Mars has two distinct hemispheric regions, the heavily cratered southern highlands and the smoother northern lowlands. It observed weather patterns, including clouds, frost, and fog, showing that Mars, while cold and dry, was meteorologically active. The mission transformed Mars from a disappointing, moon-like world into a planet with a complex geological history worthy of continued exploration. The Soviet Mars 4, 5, 6, and 7 missions of 1973 represented one of the most ambitious planetary exploration efforts ever attempted, with 4 spacecraft launched within a 3-week period. Mars 4 was intended to orbit Mars, but a failure in its braking system caused it to fly past the planet, managing only to return some photographs during its flyby. Mars 5 successfully entered orbit and operated for 9 days, returning 60 images before a pressurization failure ended its mission. Mars 6 carried a lander that transmitted data during its descent through the Martian atmosphere, providing valuable information about atmospheric composition, but contact was lost just before landing. Mars 7's lander missed the planet entirely due to a guidance system failure, sailing past Mars into heliocentric orbit. The Viking program, approved by NASA in 1968 and launched in 1975, represented the most ambitious Mars exploration effort to date. Each Viking mission consisted of an orbiter and a lander, with the landers carrying sophisticated laboratories designed to search for signs of life. The missions cost over $1 billion in 1970s currency, making them among the most expensive robotic space missions ever undertaken. This investment reflected both the technical complexity of the missions and the profound importance of their primary objective, determining whether life exists on Mars. Viking 1 entered Mars orbit on June 19, 1976, beginning an intensive search for a safe landing site. The original landing site selection proved unsuitable when high-resolution images revealed rough terrain, forcing mission planners to identify alternative sites. On July 20, 1976, exactly 7 years after the Apollo 11 moon landing, Viking 1's lander separated from its orbiter and descended to the surface of Chryse Planitia, the Plains of Gold. The first images from Viking 1's lander, received at NASA's Jet Propulsion Laboratory in the early morning hours, showed a rock-strewn desert landscape under a butterscotch sky. The images were sharp and clear, revealing individual rocks, sand dunes, and the horizon of an alien world. For the first time, humans could see Mars from the perspective of standing on its surface, a view that was both alien and eerily familiar, resembling desert landscapes on Earth, but under an alien sky. Viking 2 arrived at Mars on August 7, 1976, with its lander touching down on September 3 at Utopia Planitia, almost halfway around the planet from Viking 1. This site, further north than Viking 1, showed a remarkably similar landscape of rocks and sand, though with subtle differences in rock distribution and soil characteristics. The two landers provided stereoscopic coverage of Mars, allowing scientists to compare conditions at different locations and observe how weather patterns affected different regions. The Viking landers carried an impressive array of scientific instruments. Each lander had two cameras capable of taking panoramic images and close-up photographs of the surrounding terrain. A weather station measured temperature, wind speed, and atmospheric pressure. A seismometer attempted to detect Marsquakes, though only the one on Viking 2 worked properly. Most importantly, each lander carried a biological laboratory designed to test for the presence of microbial life in the Martian soil. The Viking biological experiments produced results that remain controversial to this day. 3 different experiments tested for life using different approaches. The gas exchange experiment looked for gases released by organisms in Martian soil. The labeled release experiment added nutrients tagged with radioactive carbon to soil samples and monitored for radioactive gas release that would indicate metabolism. The pyrolytic release experiment tested whether Martian organisms could incorporate carbon dioxide from the atmosphere into organic compounds. The results were maddeningly ambiguous. The labeled release experiment produced positive results that seemed to indicate biological activity, with radioactive gas being released when nutrients were added to the soil. However, the gas exchange and pyrolytic release experiments produced negative or ambiguous results. More puzzling, when the soil was heated to sterilize it and the experiments repeated, the labeled release experiment still showed activity, suggesting a chemical rather than biological cause. The gas chromatograph mass spectrometer, designed to detect organic molecules, found no organic compounds in the Martian soil, even at parts per billion sensitivity. This was surprising because organic molecules should be present from meteorite impacts even without life. This absence of organics seemed to rule out life, but it also presented a puzzle. What was destroying organic molecules on Mars? The answer would not come until decades later when the Phoenix lander discovered perchlorates in Martian soil, powerful oxidizers that destroy organic molecules and could explain both the Viking results and the absence of organics. The Viking orbiters revolutionized our understanding of Mars's geology and climate. They mapped the planet at unprecedented resolution, revealing the full extent of Mars's geological diversity. They discovered fog in canyon bottoms, frost on crater rims, and massive dust devils traversing the plains. They observed the seasonal growth and retreat of the polar caps, confirming that the seasonal caps are composed of carbon dioxide ice, while the permanent caps contain water ice. The longevity of the Viking missions exceeded all expectations. Viking 1 lander operated until November 1982, when a faulty command from Earth caused it to lose contact. Viking 2 lander functioned until April 1980. The orbiters continued even longer, with Viking 1 orbiter operating until August 1980 and Viking 2 orbiter until July 1978. During their extended missions, they observed Mars through multiple seasonal cycles, documenting how the planet changes over time. The 20-year gap following Viking saw no successful American missions to Mars, a period sometimes called the Mars Curse. The Soviet Union's Phobos 1 and 2 missions, launched in 1988 to study Mars and its moon Phobos, both failed, with Phobos 2 tantalizingly close to success before losing contact just as it approached Phobos. NASA's Mars Observer, launched in 1992, lost contact 3 days before arriving at Mars, a billion-dollar failure that nearly ended NASA's Mars program. These failures taught valuable lessons about the complexity of interplanetary missions. Engineers learned that spacecraft needed redundant systems, better fault protection, and more robust communication systems. The failures also highlighted the importance of incremental missions, building complexity gradually, rather than attempting to accomplish everything in a single complex mission. These lessons would prove invaluable for the successful missions that followed. The renaissance of Mars exploration began on July 4, 1997, when NASA's Mars Pathfinder bounced to a landing in Ares Vallis, deploying airbags for the first time to cushion a planetary landing. This innovative low-cost mission carried Sojourner, a microwave oven-sized rover that would transform our approach to exploring Mars. Sojourner, named after civil rights pioneer Sojourner Truth, weighed just 11.5 kilograms, but carried an impressive suite of instruments that would analyze rocks and soil across the landing site. Pathfinder's landing site selection was deliberate and scientifically motivated. Ares Vallis is an ancient flood channel, where catastrophic floods once carried rocks from the Martian highlands down to the northern plains. This natural collection of diverse rock types from across Mars's southern hemisphere provided a geological sampling that would have been impossible to achieve any other way. The mission found rounded pebbles and rocks, leaning in a consistent direction. Clear evidence of the massive floods that once raged through this channel. Sojourner's 83-day mission exceeded its planned 7-day lifetime by a factor of 12. The tiny rover traveled a total of 100 meters, not far by later standards, but revolutionary for its time. It analyzed 15 rock samples using its alpha-proton X-ray spectrometer, revealing that Martian rocks were more similar to Earth's continental crust than to the basaltic rocks expected from volcanic activity. This suggested that Mars had experienced more complex geological processing than previously thought. Mars Global Surveyor, arriving at Mars in September 1997, inaugurated a new era of orbital reconnaissance. This spacecraft carried a camera capable of resolving features as small as 2 meters across, revealing Mars in unprecedented detail. Over its 9-year mission, Mars Global Surveyor mapped the entire planet multiple times, observing changes in real time. It discovered gullies that appeared to have been carved by flowing water in the geologically recent past, possibly within the last few million years. The spacecraft's magnetometer revealed remnant magnetism in Mars's ancient crust, proving that Mars once had a global magnetic field like Earth's. The pattern of magnetic stripes in some regions suggested that Mars might have experienced plate tectonics early in its history, though this interpretation remains controversial. Mars Global Surveyor also discovered that Mars's polar ice caps contain enough water ice that, if melted, would cover the entire planet to a depth of 11 meters. The year 2001 brought Mars Odyssey, which remains operational today as the longest-serving spacecraft at Mars. Its thermal emission imaging system has mapped the mineral composition of Mars's surface, while its neutron spectrometer discovered vast deposits of water ice just beneath the surface at high latitudes. The spacecraft has also served as a crucial communications relay for surface missions, transmitting more than 90% of all data returned from Mars's surface. The European Space Agency entered Mars exploration with Mars Express, launching in June 2003. While its British-built Beagle 2 lander was lost during landing, later found intact but unable to communicate due to improperly deployed solar panels, the Mars Express orbiter has been remarkably successful. Its high-resolution stereo camera has created three-dimensional maps of Mars's surface, while its radar sounder has probed kilometers deep into the planet's crust, discovering what appears to be a lake of liquid water beneath the south polar ice cap. NASA's twin Mars exploration rovers, Spirit and Opportunity, launched in 2003, revolutionized surface exploration. These golf cart-sized rovers, each weighing 180 kilograms, were designed for 90-day missions, but far exceeded expectations. Spirit operated for 6 years, while Opportunity incredibly survived for nearly 15 years, transforming our understanding of Mars through ground truth observations across diverse terrains. Spirit, landing in Gusev Crater on January 4, 2004, found evidence that hot springs or steam vents once existed in the Columbia Hills. The rover discovered nearly pure silica deposits that on Earth only form in hot water, suggesting hydrothermal activity. Spirit also found carbonate minerals that indicate Mars once had a thicker atmosphere capable of supporting liquid water. The rover's dragging wheel, a mechanical failure that seemed catastrophic, serendipitously excavated bright subsurface soil, revealing sulfate salts that told stories of ancient water. Opportunity, landing on Meridiani Planum on January 25, 2004, immediately struck scientific gold. The rover landed in a small crater dubbed Eagle Crater, where exposed bedrock revealed clear evidence of past water. The rocks contained small spheres, nicknamed blueberries, composed of hematite, a mineral that typically forms in water. Opportunity found cross-bedded sandstones indicating flowing water, sulfate salts from evaporating water, and even possible mud cracks from drying lakes. Over its marathon mission, Opportunity traveled 45 kilometers, visiting progressively larger and deeper craters that exposed older rocks. At Endeavour Crater, the rover found clay minerals indicating that Mars once had neutral pH water suitable for life, contrasting with the acidic conditions indicated by younger sulfate deposits. This discovery suggested that Mars's water evolved from relatively benign to increasingly harsh conditions over time. The Mars Reconnaissance Orbiter, arriving in 2006, carries the most powerful camera ever sent to another planet. Its high-resolution imaging science experiment can resolve objects as small as 30 centimeters across from orbit, revealing details invisible to all previous missions. This spacecraft has photographed avalanches in progress, discovered recurring slope lineae that might indicate contemporary water activity, and identified minerals that form only in the presence of water across vast regions of Mars. Phoenix, landing in Mars's Arctic plains on May 25, 2008, made groundbreaking discoveries about water ice and soil chemistry. The lander's robotic arm excavated trenches revealing white material that sublimated over several days, confirming it as water ice. Phoenix discovered perchlorate salts in the soil, solving the mystery of Viking's ambiguous life detection results, and revealing that Martian soil chemistry is more complex and potentially hostile to organic molecules than previously understood. The spacecraft observed snow falling from clouds, though it sublimated before reaching the ground. Phoenix also discovered that the soil at its landing site was alkaline with a pH between 8 and 9, similar to ocean water on Earth. The mission provided the first direct confirmation that water ice extends from the polar caps to at least 68 degrees latitude, encompassing vast regions of Mars's high latitudes. Mars Science Laboratory, carrying the Curiosity rover, landed in Gale Crater on August 6, 2012, using an audacious sky crane system that lowered the car-sized rover on cables from a hovering platform. Curiosity, weighing 900 kilograms and powered by a radioisotope thermoelectric generator, brought unprecedented analytical capability to Mars's surface, including the ability to drill into rocks and analyze their composition in detail. Curiosity's primary mission was to assess whether Mars ever had conditions suitable for microbial life. Within months of landing, the rover answered this question definitively. At a site called Yellowknife Bay, Curiosity found mudstones containing clay minerals, indicating that a lake with neutral pH water, essential chemical ingredients, and energy sources once existed in Gale Crater. This environment would have been habitable for microorganisms similar to those on Earth. Ascending Mount Sharp, the 5-kilometer-tall mountain in Gale Crater's center, Curiosity has read billions of years of Martian history in layered rocks. The rover discovered that Gale Crater hosted a long-lived lake system, possibly lasting millions of years. Organic molecules, the building blocks of life, were detected in 3-billion-year-old mudstones, though whether they're biological or geological in origin remains unknown. Curiosity has also measured methane in Mars's atmosphere, which varies seasonally and occasionally spikes to levels 10 times the background, suggesting an active source that could be geological or possibly biological. The InSight lander, arriving on November 26, 2018, brought seismology to Mars. Its seismometer has detected hundreds of Marsquakes, revealing that Mars is seismically active. The largest detected quake, magnitude 4.7, occurred in May 2022. These seismic waves, traveling through Mars's interior, have allowed scientists to determine that Mars's core is larger and less dense than expected, composed of liquid iron, with significant amounts of lighter elements like sulfur. The Mars Atmosphere and Volatile Evolution Orbiter, arriving in 2014, studies how Mars loses its atmosphere to space. The spacecraft has observed the solar wind stripping away about 100 grams of atmospheric gas every second, a process that has been ongoing for billions of years. During solar storms, this loss rate increases dramatically, helping explain how Mars transformed from a potentially habitable world to its current state. The question of whether life ever existed on Mars stands as one of the most profound scientific inquiries of our time, driving not just our exploration of the red planet, but challenging our understanding of life itself and our place in the cosmos. This search has evolved from telescopic observations of supposed canals to sophisticated robotic laboratories analyzing Martian rocks at the molecular level, each discovery refining our understanding of what life requires and where it might persist. The Viking mission's ambiguous biological experiments in 1976 taught scientists that detecting life on another world would be far more challenging than anticipated. The seemingly positive results from the labeled release experiment, contradicted by the absence of organic molecules, demonstrated that non-biological chemistry could mimic biological signatures. This realization led to a more cautious, systematic approach. Rather than searching directly for life, missions would first establish whether Mars ever had habitable conditions. The discovery of ALH 84001 in 1996 reignited public interest in Martian life. This meteorite, blasted from Mars by an impact and eventually landing in Antarctica, contained microscopic structures that some scientists interpreted as fossilized bacteria. The meteorite also contained organic molecules, mineral features consistent with biological activity, and magnetite crystals similar to those produced by Earth bacteria. While most scientists now believe these features have non-biological explanations, the controversy highlighted both the difficulty of proving ancient life and the importance of sample return missions. Water, the essential requirement for all known life, has been the focus of Mars exploration's follow the water strategy. Every successful Mars mission has found new evidence of ancient water, from dried river channels to lake deposits to possible underground oceans. The discovery that liquid water might exist today, deep underground or in brief surface flows, suggests that habitable niches might still exist on Mars, protected from the harsh surface environment. The concept of habitability has evolved as we've learned more about life's extremes on Earth. Extremophiles, organisms thriving in conditions once thought lethal, have expanded our notion of habitable environments. Bacteria living in Earth's driest deserts, in highly acidic pools, under kilometers of ice, or in rock pores deep underground provide models for how life might exist on Mars. These discoveries suggest that Martian life, if it exists, might inhabit environmental niches we're only beginning to recognize. Organic molecules, the building blocks of life, have proven surprisingly elusive on Mars. The Viking mission's failure to detect organics seemed to rule out life. But the discovery of perchlorates by Phoenix explained this absence. Perchlorates, powerful oxidizers that destroy organic molecules, are widespread in Martian soil. When Curiosity finally detected ancient organic molecules preserved in mudstone, it demonstrated that organics can survive under certain conditions, opening new avenues in the search for biosignatures. Methane in Mars's atmosphere presents one of the most tantalizing hints of possible life. On Earth, 90% of atmospheric methane comes from biological sources. Mars's methane, first detected from Earth-based telescopes and confirmed by Mars Express and Curiosity, varies seasonally and occasionally spikes dramatically. Since methane should be destroyed by ultraviolet radiation within centuries, its presence requires an active source. This could be geological, such as serpentinization of rocks, or potentially biological, with methane-producing microbes living underground. The preservation potential of biosignatures on Mars might actually exceed that of Earth. Mars's lack of plate tectonics means ancient rocks remain at the surface, rather than being recycled into the mantle. The cold, dry conditions that make Mars hostile to life also excel at preservation. if life existed during Mars's warmer, wetter past. Its fossil remains or chemical signatures might be exceptionally well preserved, waiting for discovery. Jezero Crater, where NASA's Perseverance rover landed in February 2021, represents the current frontier in the search for ancient life. This impact crater once hosted a lake fed by river deltas, environments that on Earth are rich in biological material and excellent at preserving fossils. The crater contains carbonate minerals that precipitated from ancient lake water and could have trapped biosignatures. Perseverance is collecting samples from these deposits for eventual return to Earth, where they can be analyzed with instruments too complex to send to Mars. The rover's Sherlock instrument uses ultraviolet lasers to detect organic molecules and minerals that form in watery environments. Its PIXL instrument provides elemental composition at microscopic scales, potentially revealing chemical patterns indicative of past life. Perhaps most importantly, Perseverance is caching samples in sealed tubes, the first step in an ambitious sample return mission that could bring Martian rocks to Earth by the early 2030s. Subsurface environments represent perhaps the most promising locations for extant Martian life. Several kilometers below Mars's surface, pressure and temperature might allow liquid water to exist. Radioactive decay in rocks could provide energy for chemosynthetic organisms, similar to those found in Earth's deep biosphere. The European Space Agency's planned Rosalind Franklin rover will drill 2 meters into the subsurface, deeper than any previous mission, searching for organic molecules protected from surface radiation. The discovery of a possible subsurface lake beneath Mars's south polar ice cap by Mars Express radar observations has electrified the astrobiology community. If confirmed, this lake would be extremely salty and cold, but similar environments on Earth harbor life. The discovery of additional possible subsurface lakes suggests that Mars might have an extensive deep biosphere, protected from surface radiation and with access to liquid water. Cave systems on Mars, identified as skylights in orbital images, offer another potential refuge for life. These caves could provide protection from radiation, stable temperatures, and possibly access to subsurface ice or water. Some scientists speculate that if life exists on Mars today, caves might be its last refuge. Future missions might explore these caves with specialized rovers or flying drones. The planetary protection protocols governing Mars exploration reflect the seriousness of the life detection quest. Spacecraft are meticulously sterilized to prevent Earth microbes from contaminating Mars, which could both harm potential Martian life and create false positives in life detection experiments. Special regions, areas where Earth organisms might propagate, have the strictest protection requirements. These protocols will become even more critical as we prepare for human missions to Mars. The implications of finding life on Mars would be profound. If Martian life shares a common origin with Earth life, it might indicate that life spreads between planets through meteorite impacts, a process called panspermia. If Martian life arose independently, it would suggest that life emerges readily under suitable conditions, implying a universe teeming with life. Even finding that Mars never hosted life, despite apparently habitable conditions, would be scientifically valuable, helping us understand what makes Earth special. Biosignature detection requires eliminating all possible non-biological explanations, a process that could take years of analysis. Scientists have developed biosignature ladder concepts, ranking potential biosignatures from highly suggestive to definitive. Morphological features resembling cells, chemical patterns consistent with metabolism, isotopic ratios characteristic of biological processing, and complex organic molecules all provide evidence, but extraordinary claims require extraordinary proof. The Sample Return Mission, a joint effort between NASA and the European Space Agency, represents the holy grail of Mars exploration. Bringing Martian samples to Earth would allow analysis with powerful instruments like electron microscopes, mass spectrometers, and DNA sequencers. Scientists could conduct experiments impossible on Mars, such as attempting to culture Martian organisms or dating samples with extreme precision. The samples would be studied for decades, with new techniques applied as they're developed. The transformation of Mars from an object of distant observation to humanity's potential second home represents one of the most audacious undertakings our species has ever contemplated. This future, no longer confined to science fiction, is being actively planned by space agencies and private companies worldwide, with concrete missions, technologies, and timelines that could see humans walking on Mars within the next 2 decades. SpaceX, founded by Elon Musk with the explicit goal of making humanity multiplanetary, has developed the Starship system specifically for Mars colonization. This fully reusable launch vehicle, standing 50 meters tall with a 9-meter diameter, is designed to carry 100 tons of cargo or 100 people to Mars. The architecture envisions fleets of starships departing Earth during optimal transfer windows every 26 months, gradually building infrastructure for a self-sustaining colony. NASA's Artemis program, while focused initially on returning to the Moon, explicitly identifies Mars as the horizon goal. The lunar missions serve as proving grounds for technologies essential for Mars exploration. Life support systems that recycle air and water with near-perfect efficiency, habitats that protect against radiation, and in-situ resource utilization systems that produce fuel, water, and building materials from local resources. The Moon becomes a stepping stone, not just metaphorically but practically, where humans learn to live on another world before attempting the far more challenging journey to Mars. The journey to Mars presents challenges that dwarf those of lunar missions. The minimum transit time, using current chemical propulsion, is approximately 6 to 9 months each way, compared to the 3-day journey to the Moon. During this time, crews will be exposed to cosmic radiation and solar particle events without Earth's magnetic field for protection. The psychological challenges of isolation, confinement, and distance from Earth, where our planet appears as merely a bright star, require careful consideration and preparation. Nuclear propulsion technologies under development could dramatically reduce travel time to Mars. Nuclear thermal propulsion, where a nuclear reactor heats propellant to generate thrust, could cut travel time to 3 to 4 months. Nuclear electric propulsion, using nuclear reactors to power ion drives, offers even greater efficiency, though with lower thrust. These technologies, tested in the 1960s and 1970s but never flown, are experiencing renewed interest as the limitations of chemical rockets for Mars missions become apparent. The entry, descent, and landing challenge for human missions to Mars exceeds anything previously attempted. Current rovers use combinations of heat shields, parachutes, and rockets or airbags, but these methods don't scale to the massive payloads required for human missions. A crewed lander might weigh 40 to 80 tons, requiring new technologies like supersonic retropropulsion, where rockets fire into the oncoming airflow to slow the spacecraft. SpaceX has demonstrated this technology with Falcon 9 boosters returning to Earth, but Mars's thin atmosphere presents unique challenges. The first human missions to Mars will likely follow a conjunction-class trajectory, where crews spend approximately 500 days on Mars, waiting for the planets to align for the return journey. This extended stay, while challenging, provides time for extensive exploration and reduces the number of launches required. Opposition-class missions with shorter stays but longer total travel time might be used for initial reconnaissance or emergency returns. Selecting the landing site for the first human mission involves balancing scientific interest, resource availability, and safety. Sites near the equator receive more solar energy for power generation, while higher latitude sites have more accessible water ice. Locations with both ancient terrains for geological study and younger volcanic rocks for dating Mars's geological activity would be scientifically valuable. The site must be flat enough for safe landing, yet interesting enough to justify the journey. In-situ resource utilization will be essential for sustainable Mars exploration. The Mars Oxygen In-Situ Resource Utilization experiment on Perseverance has demonstrated producing oxygen from the Martian atmosphere, which is 96% carbon dioxide. Future systems will scale this technology to produce breathing oxygen and rocket fuel. Water extracted from subsurface ice or hydrated minerals will supply drinking water, radiation shielding, and hydrogen for fuel production. Mars habitats must protect against an environment hostile to human life. The thin atmosphere provides negligible protection from cosmic radiation, requiring habitats with thick walls or underground construction. Dust storms, while not as violent as Hollywood depicts due to the thin atmosphere, can last months and coat solar panels with fine dust. Temperature variations from -125 degrees Celsius to 20 degrees Celsius demand robust thermal management systems. Three-dimensional printing technologies using Martian regolith could construct habitats before humans arrive. Multiple space agencies and companies are developing robots that could print structures using local materials, mixed with binding agents. These structures might be covered with regolith for radiation protection, or built in natural features like lava tubes. The ability to construct shelters from local materials dramatically reduces the mass that must be transported from Earth. Food production on Mars presents unique challenges. Initial missions will rely on preserved food from Earth, but sustainable colonization requires local food production. Greenhouses using LED lighting optimized for photosynthesis could grow vegetables in Martian soil, amended with Earth bacteria and nutrients. Cellular agriculture, producing meat from cell cultures, might provide protein without the resource requirements of raising animals. Some propose that insects, efficient at converting plant matter to protein, could form part of the Mars diet. The psychological and social challenges of Mars colonization are as daunting as the technical ones. Crew selection must consider not just individual capabilities, but group dynamics. The isolation, danger, and close quarters could exacerbate conflicts. The delay in communications with Earth, ranging from 4 to 24 minutes each way depending on planetary positions, means crews must be autonomous in decision-making and crisis management. The governance of Mars raises unprecedented questions. The Outer Space Treaty prohibits national appropriation of celestial bodies, but how will this apply to Mars colonies? Will colonists remain citizens of Earth nations or develop their own governance structures? How will property rights, resource extraction, and criminal justice work on Mars? These questions, currently theoretical, will require answers as Mars colonization becomes reality. Terraforming Mars, transforming it into an Earth-like world, remains the ultimate long-term goal for some visionaries. Proposals include releasing greenhouse gases to thicken the atmosphere, melting the polar caps to increase atmospheric pressure, and introducing extremophile organisms to begin creating a biosphere. However, current estimates suggest Mars lacks sufficient accessible carbon dioxide for terraforming, and the process would take thousands to millions of years with technology far beyond our current capabilities. The ethical implications of colonizing and potentially terraforming Mars deserve careful consideration. If Mars harbors indigenous life, even microbes, do humans have the right to colonize the planet? Should Mars be preserved in its natural state for scientific study, or does humanity's survival justify transforming it? These questions echo historical colonization on Earth but with planetary-scale consequences. The economic drivers for Mars colonization remain uncertain. Unlike historical colonization motivated by resources and trade, Mars offers no obvious economic return to Earth. Some propose that Mars could become a hub for asteroid mining, or a backup for human civilization against existential risks on Earth. Others argue that the technologies developed for Mars colonization, from closed-loop life support to advanced materials, will have valuable Earth applications. Private companies are increasingly driving Mars exploration planning. Besides SpaceX, companies like Blue Origin, Lockheed Martin, and Boeing are developing Mars-related technologies. This commercial involvement could accelerate Mars exploration, but also raises questions about corporate governance of Mars activities and the balance between profit motives and scientific objectives. The timeline for human Mars missions continues to evolve. NASA plans for human Mars missions in the 2030s, while SpaceX aims for the late 2020s. China has announced intentions for crewed Mars missions in the 2040s. These timelines are ambitious and have historically proven optimistic. But the convergence of government and commercial efforts suggests that humans will reach Mars within the next 2 decades. The first Mars colonies will likely be scientific outposts, similar to Antarctic research stations, with rotating crews conducting research. Over time, as infrastructure develops and families arrive, these outposts could evolve into permanent settlements. Some futurists envision millions of people living on Mars by the end of this century. though this requires technological advances and economic drivers not yet apparent. As we reach the end of our journey through the complete story of Mars, from its birth in the swirling disk of the early solar system to its potential future as humanity's second home, we find ourselves at a unique moment in history. We are the first generation that truly understands Mars as a world with its own complex history, and we may be the last generation that knows Mars only as a distant, uninhabited planet. The story of Mars is ultimately a story about time, deep time that stretches back billions of years and forward into an uncertain but exciting future. It's a story of transformation, from a warm, wet world that might have harbored life to a cold desert that challenges our technology and imagination. It's a story of human curiosity and ingenuity, from ancient astronomers tracking a wandering red star to modern scientists planning the first human footsteps on another planet. As you drift off to sleep tonight, perhaps you'll dream of standing on the ancient shores of a Martian ocean, watching waves lap against russet beaches under a butterscotch sky. Or perhaps you'll dream of a future Mars, where city lights twinkle in the gathering dusk and children born on Mars look up at Earth, a bright blue star in their sky, and wonder what it's like to live on that distant world. If this journey through Mars's complete story has captured your imagination, I invite you to subscribe to this channel for more voyages through space and time. Like this video if you've enjoyed our exploration of the Red Planet, and share your thoughts in the comments below. What aspects of Mars's story fascinate you most? Do you believe we'll find evidence of past or present life on Mars? Would you volunteer for a one-way trip to colonize Mars? Until next time, keep looking up at the night sky, find that red wandering star, and remember that you're witnessing the next chapter in Mars's 4.5 billion year story being written right now. Sweet dreams, and may your sleep be filled with wonders of the cosmos.